Hey gang, and welcome back to another worksheet solutions walkthrough for the worksheet, synthesis practice, and more benzene reaction practice. Okay gang, so if you're coming to this video, that means you've probably seen a whole host of the benzene instructional videos, or you've, in your class, you've learned a lot of concepts, and maybe you tried to practice for this worksheet, right? And you looked at the answers, unsure of, how some of the answers were arrived at. Well, if you're looking for explanations, you are in the right place. So what we're going to do is we're just going to go through this worksheet. I'm going to show you how I arrived at the answers for the solutions I provided. So enough of me blabbering. Let's get to work. Okay, gang. So I didn't number these per se, and that's a little bit on me, but I'm going to call this kind of number one, where we have these three, provide the reagent, if you almost want to think of them like as mini synthesis problems, but, we have them, and we need to fill in how we started and how we arrived at the products. Okay, so if we take this first problem, for example, so you can work backwards retrosynthetically if you'd like. With these problems, I almost kind of like to start from the beginning and go to the end, gathering information at the end first. So that's how I'm going to go about explaining these. So first and foremost, when I look at this over here, and I see here, compare the beginning and the end, I see I have an electron donating group, strong electron donating group, right, through resonance. It's definitely going to activate the ring, and I'm going to be an ortho pair director. And we even see that we definitely need to brominate in this problem, but we know that when we do ortho pair direction, we're absolutely going to at least go para first, right, to minimize steric interactions. So what's going on here? Well, when you see a problem like this where the para position is not occupied, right, this immediately smells like you need to use a sulfonyl blocking group in your synthetic scheme, your reaction sequence, whatever you want to call it. So what I think we should do first is sulfonate this position right here. Place a sulfonyl group on there. The reagents we would use to do that would be H2SO4, sulfur trioxide. So if you want to think about it, after step one, and I'm going to use a circle right there, I would definitely have an SO3H group right there. Then I'm safe to brominate. That is when I can break out my Br2, FeBr3, right? Which I know, given this structure, the ethoxy group is still the dominant directing group, right? Because this is, if anything, a meta director deactivates. We are definitely following the orders of the O-ethyl, and we will definitely brominate on either ortho position. That gives me the bromine over there. So after that, I have my bromine right there. And then last but not least, I need to remove my sulfonyl group. And remember, we can do that. All we need is acid and heat. So H3O plus and heat wipes away the sulfonyl group, and this accomplishes the transformation. Okay? Problem two. Now when we look from here to here, I hope you pick up on a few key things. What we're seeing from here over here is that we lose the carbonyl. Okay, that's gone. And we also have evidence of a Friedel-Crafts acylation, right? Where that carbonyl is still intact, okay? So this is not the hardest problem, but we know we need to do a Friedel-Crafts acylation, and I hope the carbonyl you're thinking of looks like this. Okay? Now the thing is when we reduce this carbonyl carbon, we could also be at risk for reducing this if we've already attached it. So what I was kind of thinking with this problem is you can use your reduction method of choice first, right? So once we do this, I'll erase my work over here, we then achieve this right here, okay? And then if we were to, gauge directing-wise what we have available to us, we have two ortho pair directors. 1, 2, 3, 4, which is what we see over there, but we have symmetry here. So even if you were counting 1, 2, 3, 4, these two positions are equivalent. So really, this is just a really simple, don't acylate do your Friedel-Crafts acylation, then the reduction, because you'll lose that carbonyl as well. So at this point, then you could bring in your AlCl3 and the acid chloride you need right there. So this one, very straightforward. This, I think, is what puts it all to the test in my mind. Okay, so we have a whole bunch going on, and we start from blank old benzene, okay? So we have quite a few things. What I hope you're seeing is we have this, so we have this acetylated NH2, right? We definitely had an NH2. We threw in, we acetylated it right with an 2-carbon acid chloride. I hope you're thinking we put an NH2 on first, we acetylate it, we protect it because we're going to need to then sulfonylate down here, right? And I think I misspoke up top, right? Sulfonylate, right? Because obviously that would go para, right? And we know that would then occupy and block that position, which would then help us chlorinate over here. So what I'm thinking first is we need to get an NH2 on this benzene ring. We don't have a reaction that directly puts an NH2 on our benzene ring. However, we can first nitrate. So with sulfuric acid and HNO3, right, we will put, let me erase my work up here so I can use this. We'll have an NO2, and then again, you can use your reduction method of choice because we need to reduce, we need to make this nitrogen less bonded to oxygen. I'm going to go ahead and use my good friend H2PDC. It's always been there for me. So in doing that, you'll get an NH2, okay? Now, at this point, you might be tempted to go ahead and sulfonylate. However, right, that's a slippery slope because we know, especially from the previous worksheet, that will protonate this basic nitrogen, turn it into a meta-director, and screw everything up. It's at this point you need to bring in your protecting trick to acetylate and protect this amine, right? So let me just erase this to make some more space. It's at that point that your NH2 then becomes an amide like this, okay? Now that it's protected, less basic, then we can bring in our H2SO4, sulfur trioxide, and that will place this over here because don't forget, this is still an ortho-para director because it's an electron donating group. And then last but not least, we know this will still take directing command, and the para position is occupied. We can then bring in our Cl2, AlCl3, and that will place a chlorine right there and finish off our problem. It could be on either side, right? Okay, gang, that does it for problem 1. Now we have a whole bunch of, we have some nice acid-base goodness coming up, some complete the reactions, a mechanism, and a synthesis. So a whole bunch in this worksheet, so stick with me, and let's tackle them all. Okay, gang, rolling on into what I'm calling problem 2, right? We have 2 acid-base problems, one that I'm calling A and one that I'm calling B. So in A, we are given this structure right here, and we're told that it has a remarkably low pKa. It's saying its pKa is almost 0. And we have to explain why. Now, this, depends on us remembering what pKa, represents. Remember, a lower pKa means you are a stronger acid. And being this low, we are very strong, right? This is a very good acid. It's going to be a very good donator of H+. So remember, one tool in our acid-base toolbox is to look at the conjugate base, because if the conjugate base of an acid we are being told is strong, is the conjugate base is super weak and stable, well then that verifies everything, right? We know that if your conjugate base is super weak and stable, nature likes stability, so of course, whatever you have will donate H+ to get to that really stable state, right? If we're being told that the acid is strong. So, clearly the only acidic proton we have to work with is this one right here. So, for example, if we had some type of base, I'm going to use just some generic terminology, right, or just symbolism, if you will, right? If we showed this base grabbing H+, dumping electrons onto this oxygen, what I'm hoping for and assuming is that I'm going to be able to stabilize this charge through a crud ton of resonance. Crap ton, crud ton, I don't know why I say, I've never said crud ton in my life. Okay, so NO2, whoop, not there. NO2, O minus. Okay, so we have a charge, we expected that. Let's see what we have resonance-wise. I could swing these down, form a double bond, and then I could absolutely kick this up as a lone pair. And that's very, let me use this in black, that's very familiar resonance we've seen in all the directing group stuff we've done and seen and all that. So let me draw my double-headed arrow. I'm gonna draw this over here. So what I hope you'll see, gang, and I'm not going to be able to show you this on on every position because I will run out of space. Let me draw this a little smaller, NO2, is that each of these nitro groups, right, we know they look like this. So what I'm hoping you're going to see, right, we know if I didn't have these nitro groups, right, if I just had this benzene ring like this, you know I would get a lone pair here in the resonance with causing a delta minus in the hybrid. We would get ortho-para activation in a way, right? We've seen that resonance work itself out before. Now we have these nitro groups. So how do they affect the charges when they pop up on these positions? Well, what I'm hoping you're going to see is that there's additional resonance we can draw. Let me make this. I can swing this, form a double bond there, and kick these up. So not only do we just have the regular resonance of going around the ring, which is 3 resonance structures, but we have resonance when this charge will get to this position, the ortho. We will get resonance in the nitro group when it gets to para, and we will get resonance at the other ortho position as well. So the nitro groups, if you almost wanted to, you'd have more room on your paper than I do on this whiteboard, but I would almost just say additional nitro groups create more resonance. You could just say very weak, stable conjugate base, okay? So again, we can justify the strength of the acid by looking at the stability and the weakness of the conjugate base. Okay, so now let's take a look down here. We are now tasked with finding, and let me double check the verbiage here. We want the most basic structure. We want to rank these most basic to least. Most gets a 1, least gets a 3, okay? So again, what we can do is thinking in terms of base, right? If we see more resonance and delocalization of a charge in a given structure, it means it's more stable. Stable means weak. So the weaker bases we will find, right, 3, the weakest base will have the most resonance, and if maybe there's no resonance at all, we'll see that for most basic, okay? And if we think about in terms of charge, right, bases are negative. They will use their negative charge to grab something positive. So again, we need to think about the stability of the negative charge and everything like that, or where is the negative charge being concentrated? Now, if we take a look up here, and I'm going to actually make some space. I'm going to erase all of this so I can mark this up and really give you guys a good explanation. Okay, so let's start over here. So what I hope you're seeing is there's one difference between all 3 of these. There's one that's very different. It's this one. This is actually an electron donating group, and these are both withdrawing groups, okay? So again, I think for this, we know how this resonance works out. We're going to have a delta minus here, delta minus here, delta minus here. So really, yeah, the charge is going to work its way around and then back onto the oxygen. Now in terms of this right here, these withdrawing groups, right? So remember what this will do. This will suck electron density out of the ring. Same over here. Now remember, this puts a delta plus right here, and right here, okay? Same thing over here, delta plus, and delta plus. So one thing I'm going to see in terms of resonance is right off the bat, not only do these 3 all have the resonance where we'll be able to use the benzene ring and swing electrons out, yada, 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 right, in terms of the electron density like this, these two have one more resonance structure that this one does not. I'm going to erase this, and I'm going to draw it in green. This has 3 resonance structures in total. However, these both, have 4, and that 4th structure comes from just the group itself right here. Okay, so this negative charge is split between these 2 oxygen atoms versus being completely concentrated on this oxygen, just in terms of not involving the ring at all. So what I hope you're gonna agree with me on is, in terms of stability, this is gonna be the most unstable compared to these 2 just because it has less resonance, okay? So this, we've identified the most basic structure. So now we need to kind of determine what draws the line between these 2 in terms of stability. They create the same charges on all these positions. They have the same amount of resonance, but there's one key difference, and it's this chlorine, okay? So remember, chlorine, electronegative, and remember in terms of how they affect benzene rings, through the inductive effect, they suck electrons out of the benzene ring. This group creates a partial positiveness on this carbon. Now, what I hope you'll agree with, this chlorine helps stabilize this position when that charge is, or this partial charge right here, because it's negative, this is partial positive, we have an opposite attraction, electrostatic stabilization. So because of this delta minus, delta plus, this is the most stable, which means the weakest base. Weakest. So we drew the line here because less resonance, and then we drew the line here because of this chlorine causing some extra stability here. So we would have the least basic here, second most basic there. Okay, gang, now that we've dipped our feet way back into the acid-base realm, let's bring it on back to some electrophilic aromatic substitution reactions. Okay, gang, and what I'm calling problem 3, you're going to see 3 complete the reaction questions. I wanted to integrate some older chemistry as well as the some of the oxidation stuff that wasn't included on the last worksheet. So if we take a gander right here, and I also wanted to include when you have multiple benzene rings, right? So if we take a look right here, you can see the first step in this reaction is a Friedel-Crafts acylation. But we have a quandary, a pickle. We have to figure out if we're going to acylate on this benzene ring and on this benzene ring, because unless someone's saying excess, you're only going to do it on one, right? Your mindset should be work with the more activated ring, and that will come down to the groups attached to each ring, whether they're, donating and activating or withdrawing and deactivating. Okay, that was me to myself. How can I forget that? Okay, so if we take a look, right, remember one at a time. So right off this benzene ring, I hope what you can see is a carbonyl-carbon, partially positive. It will definitely be sucking electrons out of the benzene ring, deactivating this ring for EAS reactions. However, if we take a look over here, I think you can see we have these lovely electrons on this oxygen directly attached to this ring. This is the ring that is more activated. Once you've made that distinction, this thing is just a giant group. So we know this is an ortho-para directing for this ring, and we will absolutely be directing para at this position right there. So what I'm gonna do is I'm actually just gonna call this R in this work over here, just because I can't afford to redraw that giant thing. So I'll call this R, or I'll call it OR. OR. And then I have 1, 2, 3, 4 carbons, and remember, you get that carbonyl right there. So that is the, that's after step 1. Now, what's important, and what I'm gonna go ahead and do actually, is I'm going ahead and draw this. I'll draw this on here in a different color. You'll see why, because, there we go. Okay, so this is after step 1, right? 1, 2, 3, 4. We attached, this carbon right here. Now, for the next part, H2PDC in excess. So this to me says we are going to hydrogenate and reduce everything that we possibly can. Now, if you take a look here, I hope in your head you're thinking, yeah, this, but also beware, also this, and remember when we learned the H2PDC reaction in the first place, alkenes. I like this step because it's going to reduce this, this, and this. Okay, so our final product, I'm going to draw my rings first. We no longer have that carbonyl, and I have these 4 carbons over here. So the double bond is gone, that benzylic carbonyl is gone, and that benzylic carbonyl also gone. Okay? Now, second problem. Now, when we look at this, we're just going to take it one step at a time. We have good old toluene. It's just methylbenzene. So this reaction right here. So remember, we used NBS when we were free radical, or when we were going to halogenate conjugated systems, in terms of going through a radical pathway. But with benzene, remember, we don't have to worry about these double bonds reacting because, benzene's so dang stable. So the free radical halogenation is fair game. Remember the benzylic position, if there's a radical that has to go there, it's going to be very stable. So after step 1, we will absolutely have a bromine right here. And I could have drawn the bromine up here, just drawing it down, why not? We'll save, I need some vertical space. There we go. Now, step 2, throw back to OChem 1. I know this is a benzylic carbon. You can think of it as primary, but it's benzylic. Very sterically available. This is just going to do a quick and dirty SN2 reaction, okay? So hydroxide comes in, attacks here, displaces the bromine. After that, we have an OH right there. Third step, PCC. We're going to oxidize this benzylic alcohol to a carbonyl, and more specifically, an aldehyde. So we will have this, okay? Now, more OChem 1. This will be a Grignard reaction, right? We have our magnesium chloride. We have this right here. So remember, when you see this, think of this, right? Because then we have the MgCl with the plus charge that offsets it. So over here we have attack there, kick up of electrons. Now remember, this is an sp2 carbon. It is trigonoplanar, it's flat. This carbon right here has no preference whether it attacks this way or this way. So, and we are creating a stereocenter. Remember, racemic mixture. Just one racemic, but I'm just saying it twice. And then this is some protonation to clean up. So the product we get here, and it doesn't matter if you draw wedge or dash, I'm going to choose to draw the wedge, OH. And remember, then I have to attach this carbon. So you can see here, my 4 carbons right there. I have my OH, and remember, take care to write a plus enantiomer because the only stereocenter present is the one we created in equal amounts, right? Okay, and last but not least, I'm going to create some room over here. We have this problem where we have a T-butyl group, we have an AlCl3, so we have an ortho-para director. We know this slightly activates the ring, and it's big and bulky, so we're certainly going to be directing para for this Friedel-Crafts acylation. So after a first step, we will have the T-butyl group unchanged, and we will attach on this carbon here. There's 3 carbons in total. It's going to be para. So we have that going on for us. And then second step, a Clementine reduction, right? So after the first step, we have this. The Clementine reduction just reduces that benzylic carbonyl away. So what I'm going to do is redraw this a little bit more nicely. We have this. And now for step 3, potassium permanganate, okay? So remember what this does. This takes an alkyl group and oxidizes it to a carboxylic acid. It doesn't matter how long your chain is, it magically transforms it into a carboxylic acid if you have at least 1 hydrogen on the benzylic carbon for your chain. If we take a look here, I like this problem because you do all this work down here and it's pretty much all for naught. This just becomes a carboxylic acid, but remember, this stays unchanged because there's no hydrogen up here. That's a quaternary carbon. So your product, right, the T-butyl group just sits the entire time. And all of a sudden, you get a nice carboxylic acid at the bottom. Okay, gang, that does it for the complete reaction section for, problem 3. That's the complete reaction section. I have a really, I think, cool mechanism as the next problem. It's a good problem. It's a lot of redrawing a big structure, but I think you'll see how cool it is to be able to come up with the mechanism and explain this transformation that, you know, maybe last semester would have made you cry and run. But let's tackle that mechanism, then we have a small synthesis, and then this is over. Okay, gang, so in problem 4, we have a pretty beefy mechanism, and as you know, maybe it looks scarier and beefier than, you know, or maybe it looks impossible, but I promise you, it's really not. And in fact, you possess all the skills to accomplish this back in jOeCHEM 1. So if we take a look, well, maybe besides the ending, the EAS part, but if we take a gander right here, we do see a benzene ring and an ethoxy piece right here, so we definitely see that reflected in the product, right? We're just going to kind of do like a beginning and end comparison. And then we obviously see this ring right here with the methyl group right there, double bond, and we definitely see that bond in the methyl group right there. So that's not moving anywhere. We see, you know, the cyclopentane represented 1, 2, 3, 4, 5. What's new are these 2 cyclohexene rings. And it's important to note, right, this one is off of our benzene ring. So, you know, this is all, you know, everything we've been doing recently is EAS. Having benzene grab positivity, but, you know, things that are positively charged and attaching them to itself. So there's definitely going to be a splash of EAS. There's just some other chemistry in here we have to take care of first before we get to that portion. So, right, we have this in all of its glory, and it's important to note, remember, we are in an acidic environment. It is supercharged with H+ floating everywhere. So, I hope what you're thinking is, we're not touching this double bond. We will eventually have to use this double bond, but the first thing we should do is protonate the most basic thing we have available, which is the alcohol, okay? This, remember, oxygens are amphoteric, right? Alcohols are amphoteric. We can both donate and accept H+. That's what we're gonna do in this first step. So to save myself a whole heck of a lot of space, because this thing is pretty massive, I'm gonna go ahead and draw HOS3H. I'm gonna protonate this and dump electrons there. So what I'll do right off the bat, I'm gonna try and not run out of space as much as possible, but there's quite a lot of things going on here. And I hope I don't misdraw this because I'm kind of going off of 1, 2, 3, 4, 5, just the pattern I was looking at. So this is OH2+ now. Good leaving group. We are in a polar protic environment, and what I hope you're seeing is, yeah, this is a secondary carbon, and we can absolutely form a secondary carbon, but this is also allylic, right? It's an allylic secondary carbon. So, or I should say this secondary carbon is allylic. So this solvolysis process, super good, super favorable. So to save myself some space, what I'm gonna do is I'm gonna erase the water leaving. So what I'll do is I'll just draw an arrow down here, and then I'll even just do minus H2O, and I'll write solvolysis. Okay, so what I'm trying to say is we get a carbocation at that position. Okay, so we have a carbocation, and if you're tempted to draw resonance, when I first did this problem, I also was tempted, but do you see how this double bond doesn't move? So we should keep it put for the sake of this problem and what we're trying to prove and illustrate how this proceeded. Is the resonance, does the resonance flip and that bond move back and forth? Absolutely, right? That's the whole point. The charge is delocalized. It's very stable as a result. So, a lot of breath behind that sentence. So, what I hope you're seeing though is this double bond in proximity of that positive charge. We're absolutely going to do something here. And let me actually just make this a little farther away. Okay? So what I like to do when I see positive charge and something happening intramolecularly is to start numbering. So what I'm going to go ahead and do is 1, 2, 3, 4, 5, and 6. Okay, so what I hope you're seeing is we have the opportunity to make a 6-membered ring, which we have to do, right? So what I can do as my next step is with this double bond, and I'll make this charge a little bit, I keep drawing it in an inconvenient spot. 6 there, I'll draw the positive charge here. I'll have this double bond come over, right, because this carbocation is ready to accept. So if I draw this arrow, what I'm showing is 1 bonding to 6, because we want to form a 6-membered ring. I don't want 2 to make the bond, I want 1 to make the bond, and we'll see who then, so I hope you'll see 2 is going to lose electrons as a result. So we're not getting rid of our carbocation, we're just kind of moving it and gaining a 6-membered ring, which is what we need to do, but also creating that carbocation might help us make the second 6-membered ring. So, drawing this arrow. So what I want to do first, it might look, we'll see the best way to draw this. So I'll draw this right here. So 1, 2, and then, so 1, 2, and then the next line will be a 6-membered ring attached to my 5-membered ring. So 1, 2, 1, 2. So I'm going to draw this line down, and this will be the start of my new 6-membered ring. So I'm not promising this is going to look pretty, but I promise everyone will be hooked up and attached correctly. So let me just draw a 6-membered ring, and I'll number 1, 2, 3, 4, 5, and 6. So before I go any further, 2 is the one that lost a charge, lost out on the double bond. So as a result, 2 is now a carbocation. 5 and 6 are part of the 5-membered ring. So what I'm going to go ahead and do is draw a 5-membered ring. Oh, whoops, I put on the wrong carbons. There we go, 5 and 6. It's important to note 5 is a part of a double bond, which is right here. There's a methyl group. And now we have everyone attached correctly. You can see 6 is incorporated into that 6-membered ring. It was just a part of the 5-membered ring, but now we have that going. So, what I hope you can see now, right, we've taken care of this. I'm going to use a different color. I use purple. We need to still form the other 6-membered ring. How can we do this? Well, you can see we have a positive charge in super close proximity to our benzene ring. And not only that, to add on to this, we know this is an electron donating group. It activates the ring and it directs orthopara. Well, right, this benzene ring loves positive stuff, especially now that it's supercharged with electrons. But also remember, this para position is definitely going to be where we're going to put something first. And if we count off 1, 2, 3, 4, 5, and well, look at that. The carbocation is the 6th carbon if we start numbering from where we could add to the para position. So this is just an EAS reaction from here on out. So what I'll do is I'll erase these numbers for a second. I'll draw this arrow. The double bond in the benzene ring from carbon 1 is absolutely going to grab the 6th carbon that is now currently the carbocation. I'll draw this arrow. So what you have to trust me on is this bond is going to form, and that sets us up perfectly to have our system right there. We're just going to have to regain the aromaticity in our benzene ring. So remember, I didn't touch this bond, I didn't touch this bond. It's this bond that's now gone. I have a positive charge up top because it's carbon number 2 that was not, taking the electrons and bonding with them. So I'll go ahead and draw this right here. And remember, this is 1, 2, 3, 4, 5, and 6. It's 5 and 6 that's a part of the second benzene ring. Sorry, 6-membered ring. So you can see, I'll just keep that going, and I'll use the blue to do 1, 2, 3, 4, 5, and 6. And remember, it's 5 and 6 that are part of the cyclopentane. So double bond is on 5. So we have this going, and now the last thing we need to do, we have a hydrogen here. At long last, we can grab this back up here, bring back the sulfuric acid, which is just catalytic. Catalytic meaning it's not consumed in this reaction. We are just using it. We just used it temporarily. We're going to regenerate it. And sure enough, sorry, it's not the prettiest, but whoa, okay. Hold on. We're going to draw this a little bit better. There we go. That is our final product. So gang, I hope you think, really, it's just a lot of redrawing a big structure. It's not anything super complicated, and counting to 6. So if you can count to 6, you can redraw big stuff, then this is absolutely in your wheelhouse. Okay gang, a synthesis problem to finish this worksheet out. Thanks for hanging with me to this point. Let's finish this strong and close out this walkthrough. Okay gang, to finish this worksheet out, we need to attack this synthesis problem where we take benzene and isobutane and get this benzene ring with an isobutyl group off of it. So maybe the first thing you're thinking of is, well, you know, we can stick alkyl groups on with the Friedel-Crafts alkylation, right? However, they're prone to shifts. And given the fact that we want to attach this certain or particular piece, right, that position, which is one of these primary positions, right, we won't be able to just do a Friedel-Crafts alkylation. Plus, if we want to get very technical, remember, it's a good reaction. You probably stick on more than one group anyways. So I think I'm going to go ahead and start at the end and go back to the beginning. So the first thing I think I'm going to do, and I'm going to go down and around, is I think this was a Friedel-Crafts acylation that I then wiped the carbon away from. So as a final step, one step back, I think, and this helps out with my regiochemistry. Oh, that's too many carbons, isn't it? I think why can't I draw this the way I want to? 1, 2, 3, 4. Yeah, okay. So I had a carbonyl on that position, right? So this would absolutely work, a valid step back, and the only reagents I would need is some type of reduction reagents. You can use the Clementine Reduction, you can use Raney nickel and hydrogen. I like H2PDC, okay? I know that reduces benzylic carbon, so going this way, I know that would wipe the carbon away. So now at this point, I hope what you would think is if I do this, this would just be benzene plus something that I could, you know, an acid chloride, right? An AlCl3. This Friedel-Crafts acylation would give me this piece, right? I wouldn't have any shifts. I'd stick it on. It'd be a good reaction. So I know this comes from starting material, so I'll go ahead and box that off. I know that is taken care of. Now, how do I make this? So remember, we learned how to, and we will learn more about this reaction coming soon, but if you have SOCl2 that you then treat to a carboxylic acid, I'm actually going to go more vertical because I need more space, SOCl2 to a carboxylic acid. Then you replace the OH with a Cl, you get an acid chloride from a carboxylic acid. That's exactly what we need for our Friedel-Crafts acylation. So how do we go from here to here? Well, how do we get carboxylic acids? We get them from oxidizing alcohols, right? So I definitely had a primary alcohol, and I definitely used sodium dichromate and H2SO4 to get that done. I know that would oxidize this primary alcohol all the way to my carboxylic acid. Now, how do I get this done? Well, what's the best way to make primary alcohols? Well, good old SN2. So we're going to need a good leaving group, right? And this is a way jOeCHEM 1 throwback, but right, I know this would have OH minus, come do backside attack, the whole deal. Now the question is, the age-old question that we answered long, long ago is, what halogen do I want to do? Free radical bromination or free radical chlorination? Remember, bromine's the picky one. Bromine would go tertiary. So this is wrapped up with a little free radical chlorination to give us the primary chloride, which we then do SN2 to get the primary alcohol, which we then oxidize to the carboxylic acid, which we then replace with SOCl2, which we then Friedel-Crafts acylate, and then reduce to our final product. Gang, if you're coming here looking for answers, I hope you found them. Thank you for tuning in. If you're watching this video, that means you've supported jOeCHEM financially, and truly from the bottom of my heart, thank you. No one has to watch these videos. I'm so glad you are. I hope that means you are armed with organic knowledge. Thank you for watching now, and I hope to see you all in the next video.